Good morning. How is everyone? How was Friday's video? Put myself back in the regular spot. Okay, I thought I'd start by talking about a few of the questions that I saw were giving people difficulties, and then we'll jump right into the remainder of the lecture, and of course, give you some chances to ask questions that you were confused about on Friday's video. So I won't talk about all the questions that'll be in the solution PDF that'll be released after this video or after this lecture, and then in the video as well that explains any of the questions that the PDF might not have made clear. So the trees were well done from what I've seen so far, as well as a lot of the translations. In question 2, there was one ambiguous sentence, which was 3. So it is not the case that if it rains, it pours. So there's ambiguity with it is not the case that. So if it rains, it pours. You could say this is R, this is P, and you could set this up as R arrow P in both cases. So if you say that it is not the case that negates the entire thing, you get one interpretation that says it is not the case that the entire conditional, if it rains, it pours. But there's a second interpretation where you have, it's not the case that if it rains, then it pours. So you could also have the interpretation where you have, if not R, then P. So this is one of the cases of an ambiguous sentence with it is not the case that. So we saw something similar earlier on in the course with what was the sentence? Like it is not the case that with the woman with the red hat walks quickly or the boy with the small hat walks slowly or something like that. And there was something else in the truth conditional lecture that we just did in the video on Friday. It is not the case that Toby teaches literature and Kay teaches math. So two very similar sentences. That was the only ambiguous one. 2D is a little similar, but because they're all ands, all the interpretations will come out the same. So you could do like Godzilla is a monster and a friendly creature and does not attack cities, or you could swap them around in any order or move the brackets around in any way you want, and they all come out the same. So D really isn't ambiguous because they're all the same connective. It's sort of like in set theory how you can have something like A intersection B intersection C, and this is really going to be the same thing in the end as C intersection A intersection B. It doesn't matter how you move things around, it's all the same in the end. E. So E was tough, and I tried to give you a little hint here in gray to lead you along to help. So, in order to become a professor, it is necessary to receive a PhD and get lucky. So, I say there's a conditional here, and the question is, well, which side is the antecedent and which side is the consequence? So, it's either going to be, so P for professor, let's say R for receive, and L for lucky. So, it's going to be either P arrow R and L, or it's going to be R and L arrow P. And they give you a prompt here, and I say, if you have a PhD and get lucky, are you a professor? Or if you're a professor, does that mean you have a PhD and got lucky? So it says it's necessary to receive a PhD and get lucky. So let's ask ourselves, and I'll just write this out in English. Should the sentence be true if you become a professor but don't get a PhD and don't get lucky? So should that be true if you don't get a PhD and don't get lucky? So the answer to this one is no. If you don't get a PhD and don't get lucky, you should not become a professor because the sentence says that it is necessary to receive a PhD and get lucky in order to become a professor. So What we know about the conditional is that if we have one arrow 0, the sentence should become false. So we can use these two facts to figure out which one is the antecedent. So what we can do is we can force, um, professor to be true and RNL to be false. So I became a professor. That's true, but I didn't receive a PhD. I didn't get lucky, and we can see which conditional comes out to be false. So the first one here is going to be true because we have 0 arrow 1 in this case, and the first one comes out to be false because we get 1 arrow 0. So the first one behaves much more like our actual sentence. So P arrow R and L is a better representation of our translation than the bottom one. Because the bottom one says, oh, I didn't receive a PhD, I didn't get lucky, but I became a professor, and that's fine, that's true. But that's not an accurate representation of what the truth conditions of our sentence says. So it's a little bit more difficult than the other ones, which is why I gave a little hint in gray to help you out. But that's the general strategy for figuring that out. So are there any questions about that one? Okay, I didn't really check too many submissions yet, so that's why I don't have a general idea of how everyone has done at this point. But I did only see about 5 or 6, and it seemed like it was a 50-50 split on this particular translation. Okay, from what I did see from those 5 or 6, though, the truth tables were like really well done. Some people asked about the instructions for 4, and hopefully this was clear by now, but again, I tried to go over this in lecture just to make sure. To prove A and B jointly entail C, what you had to do was you had to translate the sentences piece by piece. So most people seem to get something like this, not D arrow, not K, S or K, and then D or S. And then you had to put these together into a form where it was A and B, arrow C, and you had to show that was a tautology. So your final column in your truth table looked something like this. It was a little big, but you just had to show that this was a tautology. And one mistake I did see people making was the amount of columns, sorry, the amount of rows. So because you had 3 variables, D, S, and K, or whatever letters you chose, you might have chose A, B, and C, you have to have 8 columns, sorry, 8 rows to get all possible combinations of truth values. If you only use 4 rows, you're not getting all of the possible combinations. So, like I said, in one of the examples, you alternate from the rightmost 1 0 1 0 1 0 1 0. You move left 1 variable, you double up 1 1 0 0 1 1 0 0, and then you move left again and you go 1 1 1 1 0 0 0 0, and you keep going until all the rows are filled. So with 4 variables, you double up again and do 1 1 1 1 1 1 1 1, and then 8 zeros after that. But if you did get this far, the truth table looked perfect from the 6 I saw. Okay, these ones were a little bit more difficult. I want to talk about D. So let me just grab the definition here and bring it down. Okay, so with D, I say you can do these visually. So one way you could do this is with a diagram. So with C, you could put C here. And we could say, let's do, for instance, C diamond C. So this would be all the things that are in both C and C. So everything in here, or everything that's not in C and not in C. So everything outside of C. So we could just use a little diagram here to find out that this first one would be equivalent to the universe. So you're essentially solving D and E at the same time, just using a picture. You could also just use two particular sets and you could work with it that way. But this would be a way that you could solve both questions at once. So then E would be the first one. With the second one, C and C complement. I guess I can't really just remove that too easily. But here's C and C complement. I need everything that's in both C and C complement. Well, nothing is in both C and C complement at the same time. Okay, so I need everything that's not in C and not in C complement. Uh, well, things are either in C or C complement at the same, well, everything is either in C complement or not in C complement. So this is just nothing in the end. Like things are in C or they're in C complement. So actually the second option would have been the empty set. So you could have done this visually. So that was a little hint there to use Venn diagrams and look at the definition to draw these out if you could. I know a lot of you from the 6 I saw again did use the diagram at first to figure out how to write it out in list notation. And then for the ontological and heterological question, this was interesting. So this was a huge issue in mathematics. This was called Russell's paradox. And the idea is that in set theory, you can create a set for literally anything. But there was this one set, which I gave you in the end, the set of X such that X is not in X, that Bertrand Russell found. And this is the one set that you cannot have. Because if you ask the question, is R an element of itself? You run into a paradox. Because if R is in itself, then it should no longer be in itself. Because once it's in itself, it no longer qualifies to be in itself anymore. And then when it's not in itself, then it should be in itself. Because when it's not in itself, it qualifies to be in itself. So however you classify it, it no longer fits that classification anymore. So because of this, Russell took a step back and said, we need to completely reinvent all of set theory. And he set out on a journey to reinvent set theory, and he did it. And good for him. We don't use it, which is kind of funny. So linguists found something very similar to this, which is the ontological and heterological distinction. And they said, oh, wow, we found this cool little paradox. And then philosophers and mathematicians said, well, congratulations, linguists, we found this as well a few hundred years earlier, and we actually did something to fix this. So that's what your little investigation was, with a little bit of priming help. So A and B, from what I saw, were good. So we run into the same issue here. If heterological is heterological, then it describes itself. So it's ontological. But then heterological is ontological. So it no longer describes itself. So it's heterological. But, then heterological is heterological, and the cycle repeats. So that's what's happening in C. It's the same sort of paradox here, where no matter how you classify it, as soon as you assign it to one group of words, it no longer fits that description. So it swaps back and forth, which is a paradox. So the word itself cannot be classified. And in D, The question in D was to sort of link that back to set theory and say, how does this word in English work the same as the set and set theory, which I just sort of described? And the idea is that with the set R, if R belongs to itself, then it no longer belongs to itself. And when R does not belong to itself, then suddenly it belongs to itself again. And this is closely related to the word heterological. Um, Autological can be defined, which you did in the first question. You said autological is an autological word because it describes itself. So um, uh, this Q is hard to word, and the answer is hard to explain. So I'm not being picky about your response. I don't know why I'm typing this, but uh, just in case you're looking at this saying, oh, maybe I didn't quite get this. Again, I'm looking more for your attempt and your thoughts here than how you're wording your responses. So that's just a neat little problem that ties real language, real English into set theory in a way that's a little bit more abstract and meta theoretical than everything else that we've looked at. So I hope that problem was um, interesting and different than everything else that we've done in this course so far. Anyways, were there any questions about assignment 3 that I didn't talk about that you have questions about?
Is the word autological autological?
Yeah, the word autological is autological. It describes itself, so it's autological. Yeah, so the rest of the answers will be available on the PDF and video at 12:30. Just because there might be some people who were a little late submitting, so I didn't want to give the answers directly at 10:30 because assignments tend to trickle in between 10:30 and 11, and I don't have a hard cutoff until 12:20. But I know who's in here, and I know which questions I cover. Okay. I mean, if you do have any questions, interrupt me at any time, but I will now ask about the last lecture. So Uh, I think the beginning is probably okay. Just as a quick reminder, what we're doing now is we're taking a look at syntactic structures, and the idea is when we build the meaning and truth conditions of a sentence, we essentially have to know what the meaning of each individual word is to get to the meaning of the phrase and the structure. So we need to know the meaning of the terminal nodes, the bottom of the tree, and then we need to know how nodes combine in order to understand what the meanings of the phrases are. So, um, are there any questions about our syntactic rules? Not only the applications, or just why we have the rules that we have. Okay, so people are generally good with the um, the predicate adjectives. That's good. Okay. Um, we'll see how this thing works when we actually apply it to trees. And this was the last thing we looked at. So we're assigning, okay, this is actually quite important, this first bit, because this is sort of the end of how we assign meanings and sets to words. So at this point, you're sort of assumed to know how to do this. And in your next assignment, which will be released today, I know it's a little bit quick from assignment 3 to assignment 4, but in your assignment, you will have to figure out how to write out a lexical meaning for a ditransitive verb. So based on what you see here with is boring and sleeps and likes, you should be able to figure out how to write out something for something with 3 arguments. And if you take a look back at the relation slide, hint, hint, hopefully it's clear how we're getting these meanings. So are we okay with how these words and these connectives are getting their meanings? If you're not, please do ask, because the rest of today will be confusing if you don't understand how this is done. Okay. I do my best to count to 10 in my head, so the YouTube people just have to double tap once and they can get to the content. Okay. So we're going to go to rules today. So this is how we build our trees. And this can look intimidating at first. Semantic trees are terrifying compared to syntactic trees. But if we just take things piece by piece and we build them node by node, they're really not that scary. In fact, once you have the syntax part laid out, all you have to do is start from the bottom and apply rules piece by piece. And as long as you stick to the rules faithfully, there's no creativity that you have to follow on your own. You just have to follow the rules. In fact, once you get good at it and you understand the rules, it's an incredibly boring and tedious process because there's nothing innovative you have to do. You just have to do what the slides and rules tell you to do. It's very computational. So I will zoom in as we do this, just because the writing is very small, but just to start, we'll stay zoomed out so I can read the rule. The rules are written abstractly, so let me read the rule first, we'll look at an example, and then we'll go back to the rule. So if A, capital big A, is a category, so when we say A is a category, this just means A is like a word category or a phrase. So anything that's not a word. Okay, and then little a is a lexical entry, so basically a word or anything else. Then what I'm going to do here is I'm just going to rewrite this rule in terms of a tree structure. So then the meaning of the structure here in this situation is the same as the meaning of the node below it. So this is what I refer to as the pass up rule. So in other words, if a node has just one daughter or one child, the meaning of that daughter or child just gets passed up to its parent, because and I'm what I'm about to say is very important conceptually. So this is very important what I'm about to say. The meaning of a parent has to come from the meaning of its kids. So because a parent only has one child, it can only get its meaning from its one kid. Therefore, the meaning of its kid has to go up to its parent. So imagine we just have this node. So let me actually zoom in on this one. So this is just our syntactic tree here. This is Jack. This is a tree where we have a noun and then we have Jack. So if we say that the meaning of Jack is Jack prime, so this refers, and let me use my thinner pens for this one, this is some individual Jack in the world. Then if we want to take a look at the meaning of the noun, So the meaning of N, the node above it has to get its meaning from just its one kid. So it's going to get the same meaning as Jack, which is just going to be the same thing, Jack prime, which is this individual. So essentially, what's happened is the meaning of the kid has been passed up to its parent. So this is like the simplest rule we have. So another example, I'll try to do another one beside it. I'll try to keep this one on screen too. Imagine, again, this is just a very simple example because we're just working with the noun right now. We have another name like, well, no, Sophie. I use Sophie a lot in the slides. So let's just say Sophie is going to be S prime. We'll just keep it simple. We'll just keep it with a single letter. Uh, then we're asking what the meaning of its parent is, the noun. Well, it only has one daughter, which is Sophie, one kid. So the meaning of the noun is going to be the same thing as the meaning of its kid, Sophie. So it'll be the same thing as the meaning of Sophie, which will just be S prime. So another reminder, Sophie is a person. Sophie is an object. So Sophie is an element here. That's why we're saying S prime. This is an object in the world because Sophie is a person. Now, two things, or I guess one thing, when we're doing our trees here, whenever we write the meanings of a node that is not just a word, we want to include the rule that we use. So in this case, we're saying that the meaning is just the child here, the daughter here, and also we want the value. So we want to know where we got the meaning from, in which case it's just the daughter, and then we want also the value, in which case which is S prime, which is Sophie. So that's why a lot of these lines, a lot of these nodes have two lines in them. So Jack and Jack prime and Sophie prime here. Okay, let's take a look at an example of an intransitive verb. It looks the same way. So imagine in our syntax, we have an intransitive verb. I can use triangles here or a line, it doesn't really matter. Sometimes it's hard to draw triangles in LaTeX, so I just use a line. Especially with these trees, it can look incredibly messy. So for clarity, I just use a line sometimes. Doesn't matter how you do it. But we take a look to the left, say is hungry. Now this isn't an element, this is a verb. So we use relations, we use sets. So the meaning of is hungry, we're looking for subjects here. So that's why we have a single X here. We're looking for subjects. So we're looking for the set of X such that X is hungry in B. Now, as we move up to the intransitive verb, it only has one daughter, so it's going to get its meaning from its daughter. So the meaning is going to be passed up to its parent. So the meaning of the intransitive verb is going to be the same thing as the meaning of is hungry. So this is the rule here. And then that means it's going to be the same value. So the set of X such that X is hungry in V. And remember, we're specifying in V because now we have situations that we're describing. So in some particular world or some particular situation, this is the meaning of that. I mean, this is where those subjects are taking place, or this is where those subjects are. So imagine we have some other example, sleeps. Okay, so sleeps could be the set of X such that X sleeps in V. Okay, and we ask ourselves, what's the meaning of the intransitive verb Well, it just has one daughter, so it's going to be the same thing as the meaning of sleeps, which is just going to be the set of X such that X sleeps in B. So same idea. The meaning of the daughter has been passed up to the meaning of the parent. You might ask, Trevor, why do you spend so much time on a rule when you're just passing it up? And again, this is more conceptually what's happening. I have one daughter, so the meaning has to be passed up to the parent. Okay, are there any questions about this rule or any concerns or comments?
Is sleeps a transitive verb?
Intransitive.
Intransitive.
Intransitive. Yeah, just a
Okay.
subject.
Okay.
Uh, Transitive verbs have a subject and an object. So transitive verbs are like X sees Y. So I'll type this out. While intransitive verbs just have subjects. So this is like X sleeps, intransitive. So you cannot do something like X sleeps Y. So like sleeps cannot be transitive. There are some verbs that can be both intransitive and transitive. So for example, you can do X eats. So that's the intransitive version, but you can do X eats Y, which is like the transitive version. So some verbs can be both, depending on how it's used. Where X and Y are like the names of like foods or people or whatever. Well, if Y is a person, it's cannibalism. If Y is a food, it's fairly normal. Okay, so this rule is used for like any generic category, as long as it's just one child. The rest of the rules are a lot more specific. So we're now going to learn the rule for transitive verbs. And this one is more complicated. But again, once you acquire the rule, you're just following the pattern. So even if you don't understand it, you can still use it. It's just when you're creating new rules, which at some point you will have to do, uh, it's a little bit more difficult. So, okay, let's look at the structure for this. So if you have a verb phrase that consists of a transitive verb and a noun. So this is the structure that we're looking at. When we have a VP, so it's like Sophia, we have a transitive verb and we have a noun. How do we deal with this? Okay. Wondering, should I show an example first and then show the rule? Uh, let's look at the example first, because we can talk through the example. So I'm going to zoom in heavily on this example. Okay, so here's a transitive verb likes. So with a verb like likes, it wants two things. It wants a subject and it wants an object. So X is the subject and Y is the object. And when we think about our tree structure for this, what is Sophia in this case? This verb phrase is like Sophia. So we're getting the object. This is the, well, that's too thick of a pen. Sophia is the object here. So when we get like Sophia, we're filling in the object in the sentence. So when we get a transitive verb and a noun, What we're essentially doing is we're taking Sophia, we're taking that object noun, and we're filling in the Y position in our pair. Because Sophia is an object, Sophia is an element, Sophia is a person, and that transitive verb is looking for pairs of subjects and objects. But Sophia is now that object. So when we get our verb phrase likes Sophia, we no longer need to hunt for objects. We only need to hunt for subjects. So what our rule is going to do, our rule is going to say, okay, now for VPs, we no longer need to hunt for objects. Instead, what we need to do is we need to hunt just for subjects. So the VP says, okay, now we're looking just for sets of X. We're looking just for subjects X, where the pair with X and this noun, which was our object, is in the transitive verb. So basically what's happened here is this was the old Y. This was the object in our pair, and the Y has been filled in. So this object is filling in our Y position. This is sort of an intermediate step. This is just a demo to show you what's happening. And this is our value. This is our paraphrase. So in the end, our verb phrase is saying, okay, now I'm just looking for the set of X such that X like Sophia in V. So our final value for the verb phrase mirrors something that looks a lot more like an intransitive verb. And it also looks a lot more like the English phrase like Sophia. Because when we think about what we have at this point in the tree, we have a verb phrase like Sophia. It just needs a subject left. So we're just hunting for subjects. We're looking for the set of X such that X like Sophia in whatever situation we're in. So when we take a look at our rule above, this is what we're saying. We're saying the meaning of this is at this point, we're just looking for the set of X, the set of subjects, such that such that the pair X, and I can highlight this. This is our object, was in the original transitive verb. So this one is a little bit more abstract than the others. But if you think about this as an object substitution, maybe this isn't quite as difficult to grasp. So why don't we take a look at this in action one more time. So let's look at this without the actual semantics on the right side. Now let's just talk this through. Okay, so we have ghosted Dave and ghosted Dave. So this is our VP up here, this is our transitive verb, and this is our noun. So ghosted is looking for pairs X and Y such that X ghosted Y in V. Okay, and we're going to call Dave D prime. So I should actually, well, this is fine. D prime. So what's going to happen is for our VP, we're now getting this object. We're getting Dave. So we're going to take this object and we're going to say we're no longer looking for the object anymore. So we can substitute in Dave into this object position in Y. So for our VP, what we're going to say now is we're going to take a look for the set of X where the original pairs were in our transitive verb. So originally in ghosted. But specifically, we know what our object was. So we know it's going to be the specific noun. We know it's going to be Dave. So I don't have to specify that it is Dave at this point. I can just skip to the final value. So I can say, okay, I'm just looking now for the set of X such that X ghosted D prime, which stands for Dave, in B, because I know who my object was. And if we compare directly what these two look like, we can see they look very, very similar, right? The only difference is instead of saying X ghosted Y in V, we have X ghosted D prime, and we're no longer looking for that Y anymore. So we don't have pairs of X, Y because we're not looking for objects. We just have X because we're just looking for subjects. So the thing to the right is the same thing that's written out, just an extra step is shown in. But I figured I'd just go through that one for you and write it out piece by piece because maybe it's a little bit nicer to follow along than just to have something that's already pre-written for you. So are there any questions about this rule for transitive verbs? Okay, so what's probably going to happen with these is you might understand it now or get it, and then when you do the tree yourself, you'll have to refer to it, and things might get a little bit hazy, and uh, that's that's normal. So don't worry about that too much at this point. The more you practice, the more familiar you get. So at this point, we can do everything except for the S nodes. That's how limited our syntax is at this point, but that's pretty good so far. So one thing to keep in mind again, I reiterate this a lot, but conceptually this is important. Um, nouns, noun phrases. Well, we don't have noun phrases yet, but nouns and people are objects. That's why they're things like D prime and S prime and Sophie prime. Verbs, intransitive verbs, transitive verbs, VPs, these are sets because they're relations. Sentences are going to be truth values. So now that we go into sentences and sentences with the operators, these are now truth values because these are declarative sentences. These can be true or false. So each of these components grabs from a different thing in mathematics. So it's interesting to see how these all combine and give us, different things here. So sentence has a condition. So we're now looking at uh, this case when we have an N and we have a VP, this particular rule. And here's what we say. We say it's going to be true if the value of the noun is an element of the value of the verb phrase. So remember, the verb phrase is a set looking for subjects, and a noun is an element. So basically, if the noun is a subject for the verb phrase, it's true. So for example, I'll keep the definition up top while we go through this little syntax tree. So we have a sentence, Jack sleeps, we have a noun Jack, and we have the verb phrase sleeps. So I mean, really sleeps is an intransitive verb and also a lexical node, but at this point in the tree, I'm assuming that sleeps is the VP. And then Jack is the subject here. Okay, so Jack at this point would be like J prime, sleeps would be the set of X, such that X sleeps in V. So I'm just going to write these out by hand at this point and just walk through them with you. They're already written out nicely if you want to refer to the pretty ones, but I'll just write them out. Okay. So um, the S is true if the noun subject is an element of the verb phrase. So I really should be saying the value of the noun is an element of the value of the verb phrase, but I'll just say if the noun is an element of the verb phrase. So we can really just replace these with each of these nodes. So the value of the noun is just J prime. So this is saying if Jack is in the element of the value of the verb phrase. So if Jack is an element of the set of X, such that X sleeps in V. So, I mean, this makes sense, right? If Jack sleeps is true, then Jack should be an element of the set of X such that X sleeps in V. In other words, Jack should be a sleeper. Now, in English, you might think, well, what's the point of this? This doesn't really give us any insight. But computationally, you can understand why this would be helpful for a computer to analyze that language. You give a computer a set V that contains a bunch of information about the world, who's sleeping and who's not sleeping. You want the computer to figure out who's sleeping, if Jack sleeps is true. So it has to check this database of all the sleepers. It checks to see if Jack is in that set of people who are sleeping. If Jack is in that set of sleepers, then yeah, it comes out true. So it's a little bit more computational than how this would work in the brain. So if you're thinking, Trevor, is this how truth conditions work in the brain of humans? That the answer is no. This isn't how it works in the brains of humans, but this is how computers can do it. So this is how truth conditions works for a sentence. It's true if and only if Jack is if Jack is an element of sleepers. Jack is an element of the set of X such that X sleeps in V. What if the VP isn't intransitive, but it's transitive instead? Does anything change? And the answer to that is no. Nothing changes in this case. We can still have an S, an N, and a VP. So if we write things out, this would still be J prime, likes Emily. So this is a transitive verb, but it's a verb phrase at this point. So the verb phrase at this point is just looking for the set of X such that X likes, let's say E prime for Emily in V. So at this point, it looks like an intransitive verb because it has that object already. It has Emily. So at this point, in Jack likes Emily, this is going to be true if the value of the noun is an element of the value of the verb phrase. So same rule as before, exactly the same rule, same application. Just because we have a transitive verb in the verb phrase, nothing is changing. So this is going to be true if and only if J prime is an element of the set of X such that X likes E prime in V. And that would be the value of the sentence. That's how we know the truth conditions. When is Jack likes Emily a true sentence? Well, it's true if Jack is an element of the set of X such that X likes Emily in some situation B. Okay, are there any questions about how we did the rules for sentence truth? Okay, what we'll do now then is we're going to do a 10-minute break. We'll do the rules for the operators after. We'll do a sample tree, and then we'll do one practice tree. Uh, the practice questions actually have two trees. So what I'll do is I'll do one in lecture, and then there's going to be a video that I recorded from the previous semester with the other tree on it. So I'll link that one with that tree, or you can do it yourself and you can check it, but the trees are fairly long to do. I'll talk about that again later, but I'll give you a 10-minute break, so I'll see you at 11:30. If you have any questions, as always, type them in chat, or we'll talk about them when I get back. Oh, what a beautiful $75 million house. Okay, two more rules to go. These are for our conjunctions. So what these rules do is they basically take the sentence truth value and they modify it exactly how you would expect them to based on the conjunctions. So for these ones, I don't think I need to actually do them step by hand, but I will go through how the rules are written. So what the negation does, and I have a little bit more space to draw them, so I can actually draw them at the bottom. This looks at the case where we have an S, we have a negation, and then we have another S. So what this does is this says we're going to take the negation operator and we're going to apply it to S. And what happens, of course, is it takes any ones and it turns them to zeros. It takes any zeros and it turns them to ones, and it applies it to the sentence. So this rule is actually a function. So this might look a little bit different, or it might look different because of how many double brackets we have, but this is really like saying f of x. It just looks a little bit more intimidating because there's a lot more notation going on. But it's applying a sentence to a function and it's changing what happens to x. So if s is true, then the function is saying, okay, but now s is going to be false. If s is false, the function negation is saying, okay, now s is going to be true. So the sentence that we're looking at now is, it is not the case that Jack sleeps. So it is not the case that is our negation, and Jack sleeps is our sentence. So let's zoom in on our sentence right here. So this is Jack sleeps. So Jack sleeps is going to be true if Jack is in the set of x such that x sleeps in V. So this is what we did before. And our negation is a function that turns 1 to zeros and zeros to 1. Okay, so what happens when we combine these together up top and we get, it is not the case that Jack sleeps. Wow, look at that, perfectly, right at the top. Our rule is in line 1. So this is our rule. We're saying that we're applying negation to the sentence. And you can end with either of these steps. So 2 isn't an intermediate step here. So 2 here, this is the value. You have a choice of how you want to end it. This is preferred. Usually it's better to end a sentence by saying when it's true rather than when it's false. But what we can say is we can say that it's false. So we just flip the value here. It's false if Jack is in the set such that X sleeps in V. If we say it is not the case that Jack sleeps, well, then it's false if Jack is someone who sleeps. Alternatively, we can say that it's true if Jack is not in the set such that X sleeps in V. So what we've done here is we've said it's true, but then we've also made it so Jack is not an element of the set of X such that X sleeps in B. So we've done two alterations here. It just depends what we want to negate. Do we want to change the truth value and say it's false if Jack is in that set, or do we want to say that it's still true, but change the conditions on whether Jack is in that set or not? Um, there are advantages to this approach. Um, so here's the advantage, and I won't write this because there's not enough space and it'll get cluttered, but the advantage to this second approach, and I'll say this slowly, is that if a sentence continues on, like there's more nodes above it in a tree, all of the rules are based on whether its children or daughters are true. So if you have to keep building up further in a tree, it's easier to apply more rules if your nodes are based on when things are true. So writing everything's in terms of truth just makes further rules and applications easier. So if it's the final node in a tree, ending it in 0 is okay. But if you have to keep working, finish it with a 1. Okay. So this is the rule for negation. Let me keep that in a little bit closer. So it just flips the truth value, just like in logic. Are there any questions about this one, or can I just keep going?
So when we're drawing the tree, we need to write the rules and the values.
Yeah, rule and value.
Okay.
I think on the assignments I have that specified so that way you don't have to keep that idea in your head. It's always there to remind you. Okay. Last one is conjunction, and it works very similar. So we have uh, Jack sleeps and Kate is hungry. So how this works um, is we have a sentence, we have two more sentences, and basically what we're doing is we're applying a conjunction function to two sentences. So usually we say this is like S1, and then we have S2. And what's happening is these are in a specific order. So order does matter. So it's an ordered pair here. So 1 and 2. And as you remember from the truth table before, or from the and function, how it's defined, we'd say like if it's and, then 1, 1 gives us 1, 1, 0 gives us 0, 0, 1 gives us 0, 0, 0 gives us 0. So depending on the truth values of each one in our pair, we get a different output, and that's how it defines what the value is for our sentence pair. So if we, sorry, we zoom in on our example here, uh, this is S1 in our case. Sorry, I did zoom in a little bit quick, but this is essentially the same thing. This is Jack sleeps, and this is Kate is hungry. Kate is hungry. Okay. So, and this is and. So the reason I zoomed in so quick is just because we have the same information here. So this is the truth table for and. It's just in function form. So it's true only in the first case when both Jack sleeps and Kate is hungry is true, and it's false in all other cases. So in the first line, we're basically saying uh, we're applying the conjunction to the two sentences, S1 and S2. So S1 is Jack sleeps, S2 is Kate is hungry. Order does matter. So the left sentence is S1, the right sentence is S2. Uh, Order matters, especially if we do conditionals. We don't have conditionals in our rules because technically they're treated a little bit differently and more advanced. You might see them in an understanding and extension problem in the future. Maybe. I'm not sure yet if I want to do it. But if we did have conditionals, order would matter, especially for them. So there's an intermediate step here that says one if S1 is true and if S2 is true. That's how AND works. So when we translate that over into um, our conditions here, this says, okay, this has to be one if Jack is in the set of sleepers and Kate is hungry. So this is like saying S1 is true and S2 is true. Now, if this were or instead of and, then what you would just do is you just write or instead of and there. So uh, in the end, we still kind of use natural language in our description, but the details in the truth values are actually kept in the function itself. So the details of what is true when it's true are kept in the tree, but when we talk about the values of the S node, it is written more in natural language. So some of you in computing science or cognitive science might think, well, it's a little bit less rigorous when we talk about the final value for the sentence node. And yes, that's true, but the rigor is kept within the tree. It's just in the conjunction node rather than in that final value in the S node. So the conjunction was a little bit faster than the others, and same with the negation. But um, you all seem to be doing quite well with the truth tables, so I figured that um, you might not struggle so much with this. But if I'm wrong, please do let me know. So, are there any questions about these operators with these trees? Can you try doing some yourselves? So I'm going to. Uh, okay, you will have an opportunity to. I'm going to show you one example and then we'll do a practice question. And while I'm doing the practice question, I guess you can try to do it at the same time as me. But because it's such a long practice question, we have to do it simultaneously. Otherwise, I just can't do the solution at the same time. Uh, I guess I can hide my screen while you work on it and then I can show it after. I think that, yeah, that'll be a good way to do it. Okay, so here is an example sentence. It is not the case that Sophia likes James. And I say it's intimidating compared to a syntactic tree because, again, there are more lines. And if I showed you this first, yeah, it's a little bit more terrifying. But like I said, um, as long as you can set up the tree with the syntactic rules and you can assign values to all the nodes at the bottom of the tree, all of the words themselves, then all you have to do is find the rules and apply the rules piece by piece, and you can get to the top of the tree. Even if you don't understand the rules, as long as you know how to apply them, you can do it. Which is sort of unfortunate in a way, because understanding the rules is how you come up with new rules, which is something that you will have to do in one case in assignment 4 and in a couple cases in assignment 5 and 6. Um, So when we talked about how the transitive verb was done, where we have this object and we replace the object in the pair, like that's an important concept that you'll have to do with the ditransitive question that you'll have to do this week. So if you didn't quite catch that, you'll probably have to watch the recording again. Anyways, oh, sorry, that's not the button I wanted to press. I wanted to zoom in. Let's take a look at the sentence. It is not the case that Sophia likes James. So what we do first in these is we give values to all of the bottom nodes. So what I've done here is I've used full names because I typed, but if I did this by hand, there's no way I'd type James, or no, there's no way I'd write James Prime. I would write J prime because my hand would hate me by the end of it. And I encourage you to use just capital letters for people. Don't write the full names. Okay, so I gave James prime here. Let me use a different color. J prime, James prime, and likes. So likes is transitive in this case. It has an object. So I have pairs x, y, where x likes y and v. Because I have more than one noun in this sentence, and I have more than one sentence node, what I've done is I've given each n a different number. That way I can just give them, that way I just know which one's which. And that way when I apply my rules too, I know which one is being applied, which n I'm applying it to. So I encourage you to do the same thing as well. So uh, these rules are fairly straightforward because they only have one daughter. So with n2, n2 is just going to take the same value as its daughter, so it gets James. So I have my rule here, and then I have the value. So n2 is the same thing as James, which is James prime. With the transitive verb, one daughter, so it gets the same value as likes, which is the set of pairs x, y, where x likes y and v. So likes and James, a good start. The first thing that we really have to do is the VP. So at this point, remember we have the verb phrase likes James. So sometimes it's good to actually write out the English because we have likes James. So in your mind, you can think, okay, the English verb phrase is likes James. This has an object. So I don't need objects anymore. So what you've done at this point is you've taken James and you put it in this object position. So the rule says now that we're just looking for subjects X, where the pair X and that object were an element of our original transitive verb. So in other words, instead of XY in likes, we have X and that object in likes. So we have James in likes now. So our verb phrase is just looking for the set of X such that X likes James prime in V at this point. So this is our paraphrase. That's our value. And the first one is our rule. The second one is an intermediate step that we don't have to include, but you can include if you want to. Okay, we have a verb phrase. So the other important thing here to remember, the verb phrase can only be built from the meanings of its daughter. So it's just taking the meaning of likes, the transitive verb, and James. So now if we want to go up and we get the meaning of the sentence, Sophia likes James, we know the meaning of the VP, but we still have to get the meaning of the noun. So we have to take a look at Sophia here. So Sophia is a proper name. Great, we can just say that Sophia prime. The noun is going to get the same as the meaning of its only daughter, which is Sophia. It's a proper name. The more you do proper names, you just sort of write them all in one step. Okay, so the same thing as James. Okay, now at the sentence level, sentences are truth values. So we have a full sentence. This is Sophia likes James. We could think, okay, now that we have a full sentence, we are in the realm of propositional logic. So these should now be truth values. So this is now one if and only if the noun is an element of the verb phrase. So if our subject, Sophia, is an element of the set of X, such that X likes James prime in V. So that's when the sentence is true according to computers. If Sophia is in the set of X such that X likes James prime in V. So if the sentence was just a simple declarative, we would be done there. However, that's not the case. That's not just a simple declarative. We're still negating the sentence. We're saying it is not the case that Sophia likes James. So at this point, we have to do the negation. The negation is an operator. So this is going to be a function that takes ones to zeros and zeros to ones. The negation, this really should be a triangle, but that's okay. It still just has one daughter, so it's going to take the same value as the daughter. It is not the case that, which is the function. I know sometimes the functions are a pain to rewrite, but we do just have to rewrite them. It's a little bit easier on a computer, but it's also harder to type on a computer. Okay, so then going up to that final value when we combine it both. So the sentence 2 is taking the meaning from sentence 1 and the negation. So it applies the negation to the sentence. So what I've done here is I've just flipped the truth value. Instead of saying it's true if Sophia is in the set, now I've just said it's false if Sophia is in the set of X, such that X likes James and V. And because it's the final node in the sentence, I've just left it as a 0 because I'm not doing any more building, so I have no reason to change it to 1. But I could if I wanted to. So another way I could change this or end it is I could say it's true if and only if Sophia prime is not an element of the set of X such that X likes James prime in V. That would be another way to write that final line. So that would be a full tree for a sentence with our small fragment of English that we can work with. Again, it's not a very interesting fragment of English. The sentences don't get very amazing, but this is what we can do. Do you have to go bottom up when doing this? You don't have to go bottom up. You can go top down. But that does mean that you have to know how the rules apply before you, well, you have to know the result of the rules before you apply them. So if you know the rules well enough that you can go top down, you can, but the application of the rules, the algorithm assumes that you go bottom up. So the algorithm and rules are set up in a way that they can only be applied bottom up. Yeah. Yeah, it's like in syntax how the rules are set up, so you're supposed to do the rules top down, but you can do them bottom up. It's sort of the opposite for semantics, where the rules are set up so you're supposed to do them when you start from the bottom and go up, but you can do them top down if you know them well enough. But I would, unlike syntax, where we usually recommend you do bottom up first, I recommend in semantics you always do them bottom up. Um, some people in syntax do a lot better when you say, no, have the freedom, do them top down. I don't ever recommend doing it top down unless you're extremely confident. Okay. Were there any questions about this example? I'm maybe I shouldn't have zoomed out so much. The way syntactic rules are constructed, the way they're set up in phrase structure grammar is to do them top down, at least at the 220 level. That's how they're set up. Um, Semantic rules uh, are set up in a way where they're constructed to be done bottom up. But usually when you start doing syntactic trees, you start by labeling word categories first, and then you build them bottom up. So even though the theory, so even though syntactic theory is built top down, typically students start bottom up, while semantic theory is constructed to be bottom up, and we teach it bottom up.
You're not picky about us using triangles or lines, right?
No, not in this course. Okay, one final thing here is about truth values. So, uh, I mean, there's not really anything more to say about truth conditions, but we can still analyze the situation. So we can say, if we have a situation where Sophia likes James, and we have this tree or the situation, uh, is the sentence true or false? So we can still apply things we did in propositional logic to this. So if Sophia likes James, and we have the sentence, it is not the case that Sophia likes James, then that sentence would be false because Sophia likes James. So you'll see some questions like that on your fourth assignment. And I'll make sure on Friday that if there are any questions about that, I address those because the one of the questions might be a little bit confusing just because the notation's a little bit different than what we've seen. Okay, so that's it as far as content. I mean, this is the end of the truth conditional meaning of sentences lecture. Unfortunately, this is all we can do with our syntax. We can't do, I mean, we could try to do adjectives. In your homework or your assignment, you're going to do ditransitive verbs. In an understanding and extension question next week, you're probably going to do adjectives or CPs or PPs or something like that. I'm not quite sure which one I'll give you. But F1 is pretty limited. What we want to do is we want to do something like determiners. We want to add common nouns like dogs and cats, um, some, every, all. But the system that we have with propositional logic, we don't have the tools for that yet. So what we're going to have to do on Friday and next week and over the course of the next 2.5 weeks or so is figure out the tools that we can uh, get in order to add determiners and common nouns into our system. And also in logic, it wasn't very satisfying that if we have something like uh, Dave likes Charlie and Dave likes Steven, well, that would have to be like P and Q. It would have to be two separate variables, but the sentences are so similar. Why would a logic system need two completely different symbols for two sentences that are so similar? So, uh, what we're going to do is we're going to revisit a new system of logic in the next 2 weeks, and then we're going to get a new fragment of English called F2 that can do so much more. And that can also deal with scope ambiguity, which this system cannot. So this is sort of an introduction to how we do it with a very boring fragment. But now what we can do, if you don't want to stay for the practice, you don't have to stay, but I would like to give you some time to work on this sentence. It is not the case that you dislikes Carol or you is hungry. So for this one, you can set up the syntactic tree and you can try to draw the whole semantic tree for that. So you give a meaning to each node, a value to each of the lexical nodes at the bottom. You give the rule and value for each of the nodes going up in order to give a truth condition to the final sentence. I don't know if you'll be able to complete the entire thing in 20 minutes for the first tree. Um, might be quite difficult to do, actually. Usually the first one takes about 20, 25, 30 minutes to do, but we'll see how far you can get. Uh, I'm trying to think how I can do this at the same time as having this on screen. Because I want to draw this at the same time that you're doing the question. But if I do the question, then this doesn't show up on screen. Hmm. Okay. Um, okay. If you want to try this, go ahead. I think what we'll do is I'm just gonna work through this for the next 20 minutes. If you want to work at it at the same time, feel free to. If you want to mute, go ahead, and then you can just take a look at the recording again after if you want to check your answers, or you can just check in periodically as I work through it. Maybe that's the best way to do it. And that way, the solution's here for everybody in the video, and there's not a long pause. So let's just do that. For the next 20 minutes, I'll work through the solution. And yeah, if you want to work, feel free to mute me or just have me on in the background. So write down the sentence if you haven't, if you don't want to see it on screen. I'm actually gonna do this one. I will link a video that I recorded in the fall semester with 17. So I did 17 in another video. The reason I'll link it is because it takes about 20-25 minutes to do the whole tree. So it's already done once. Okay. So I need a page that's super wide. And then we'll start at the bottom. Okay, so my hope is that I don't run out of space here, but I could. Okay, so is hungry is an intransitive verb. And for this, I'm also going to just get rid of my face here. I'm going to get rid of the webcam because I need as much space as possible. Okay, so is hungry is an intransitive verb, so we need to give this a lexical entry. So this will be the set of X such that X is hungry and we're in a situation. So I'm going to say in B. For the sake of time, I'm also going to abuse a lot of copy and paste. So I'm sorry if you can't do that, but I'm going to abuse the tools I can abuse. And I encourage you to abuse whatever tools you can as well. Okay, I'm also going to use my line tool here to make things as nice as possible. Okay, so this will go up to an intransitive verb node. And the way that the intransitive verb node works is it will take the same value as its only daughter. So this will take the same value as is hungry, which is just going to be the set of X such that X is hungry in V. Okay. I will try to glance at the chat as much as I can as I go through each node. So if you do have a question, you can interrupt me or you can type or whatever. Okay. At this point, this is going to join in with an S. Let's write the S a little bit above, but I need a noun first. So I need my subject here, you, but I don't have the daughter yet for you, so I should fill that in. So you, I'm just going to call this y prime. So that noun is going to be the same value as you, which we'll call y prime. Okay. Now this is my first noun that I have so far called, so I'll call this N1. I'm going to call this sentence S1 as well. So my sentence is going to be true if and only if that noun subject is an element of my verb phrase. And I'm just remembering I haven't done the verb phrase yet. Okay, so this is why we have the tools. So this should be part of the first verb phrase I have. So we'll have to move some things up. Ah, this is the joys of technology. Sometimes we forget things. So the VP has only one daughter, which is the intransitive verb, which is going to have the same value as is hungry. But, oh, that's the only space I have. What is happening? That's not big enough at all. Oh boy. I thought I made a bigger thing than that. Oh, that's awkward. Okay. So we have this node. We have the sentence node above. That's going to go here. We're going to get there. This will go up here. So this will be true if and only if U is an element of the set of X such that X is hungry in V. Okay. So this is just the right side, but this is U is hungry. So U is hungry is true if U is in the set of X such that X is hungry in V. So that's the right side. And we made that a little bit too big, but I'll keep that on screen for now and I'll shrink it when we need more space. Okay, so now we need to do U dislikes Carol. So what I will do actually for now is I'm just gonna move things a little bit closer together. So one thing I recommend doing, and I apologize for saying this a little bit too late, but when you do this on a page, use your page horizontally. Just like turn it on its side and give yourself as much room as possible. Because sometimes these things get pretty big. Okay, so U dislikes Carol. So I'm going to zoom in. Okay, so we need Carol here. Which we'll call C prime. We'll call this N2, which will get the same value as Carol, which we'll call C prime. Dislikes is a transitive verb. So this is going to be a little bit harder to fit, but we'll try our best here. So this will be pairs x, y, because it's transitive, where s, x dislikes y and v. And I'm going to copy that because I'm going to need it. We can move that over there, but that's going to take up a lot of space. So we're going to have to do some more moving around here. And we're going to have to shrink this just a little bit. Okay, so let's copy that again. Okay, so when we do the meaning of the VT, it's going to be the same as the meaning of dislikes, which is a set of pairs x, y, such that x dislikes y and v. At this point, we can now make our verb phrase. So when looking at the meaning of the verb phrase, we now have a rule because we can't just do the pass up rule. The verb phrase has two daughters. It has the VT and it has the noun object. So we're no longer going to look for objects because what we're going to do is we're going to take this object Carol and we're going to substitute it in for the Y position, the object position. So what we're doing now is we're just taking a look at subjects. We're just finding the subjects X, where X and the object Carol, so in this case N2, is in that transitive verb. So what this now looks like is the set of X such that X dislikes specifically Carol, so C prime in V. Okay, so it's not the case that U dislikes Carol. So at this point, we need to introduce U again. So I know that we already have a value for U on the right side of the tree, but we still need to introduce U again because it is a syntactic tree. So U dislikes Carol is a sentence on its own. So we need to introduce U again. So let's take a space. Let's do U here. So U is going to be Y prime. Let's use the tool again. We're going to also give this a different node value. So N3, which is the same thing as U, which is Y prime. And this will be another sentence. Okay, so we'll call this sentence 2. And same rule. So even though we have a transitive verb in this case, it's still going to follow the same rule. This is going to be true if and only if our subject, so in this case N3, is an element of our verb phrase. So in this case, I should call this VP2 because we already had a VP1 on the right side. So if VP2, if N3 is an element of VP2, so this is true if and only if U, which is Y prime, is an element of the set of X, such that X dislikes C prime in V. Okay, so now we have the little mini sentence here, U dislikes Carol. Okay, but we're not done yet. We need to do, it is not the case that U dislikes Carol. Okay. So I gotta take this, I gotta shrink this a little bit. I can move this over a little bit. And now we need to do, it is not the case that. The fact that I can fit this on one standard slide is nothing short of phenomenal. But also, what a mess. It is not the case that. Okay, it is not the case that. Let's do that here. So this will be 1 to 0 and 0 to 1. This is a negation. So I should use my triangle for this. So I'll use my triangle here. Okay, so that's just 1 to 0, 1 to 0, or 1 to 0, 0 to 1. It's a function. So the negation, we can't forget the negation. The negation is a category. It is not the case that is a word. So usually what I see when people start is they just do one or the other, but you do need the category going to the word. So we do need to repeat and say the negation is, it is not the case that. Yes, it's a pain, but that is the rule. So 1 to 0, 0 to 1. Okay, so we have this done. And now we can create sentence 3. Now sentence 3 is built from its two daughters, the negation and sentence 2. So the rule for this one says we apply a function of the negation onto the other daughter, which is S2. So what this does is it flips the truth value. But I have one more thing after this, the conjunction. So I want this to be in terms of 1 rather than 0. So instead of saying it's 0 if U is in the set of X such that X dislikes Carol, I'm going to say it's true if and only if U is not in the set of X such that X dislikes Carol or C prime and V. So what I've done here is I've said that U is not in the set rather than saying that U is in the set because I still have one more step to go. Yeah, the tree is massive. That's why I said it's intimidating. But if we go step by step, we're just applying rules. That's all we're doing. So the trees in the lecture later are even scarier. But again, it's just a process. It's just a process. What I say, everything in this course is really intimidating in terms of looks, but conceptually, it's 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 along the same terms as phonology. It's just that because there's so much notation, it's a lot more intimidating, which makes it seem a lot harder. Um, okay, so at this point, we have it is not the case that you dislikes Carol on the left, and on the right we have you is hungry. So we just have to combine these together with or. So to do this, we have to move some things around a little bit. We have to make some space. Uh, I wish I had a little bit more space, but the program just does the slides like this. And anyway, it's massive, but it's not as difficult as it looks like. What if this is on the test? Um, what if this is on the test? Uh, there will be a shorter one on the test. Okay. Where were we? Or. The last thing we have to do is or. Okay. I'm doing or in purple just for the sake of space and clarity. It's definitely better to handwrite it. Do not type these. It is so much longer to type these than it is to handwrite these. Uh, and if you're messy too, I don't care if you're messy. I can figure out if you're messy. I'm trying to be a little bit neater because I'm writing for you. If I do these by hand, I can pump out this whole tree in like 3 minutes. It's not pretty, but uh, if you're fast, go for it. Um, be messier. That's fine. I'm not looking for beauty. I'm just looking for the fact that it's there. So the or is a function. It's a truth table. It's true if at least one of its disjuncts is true. So that's 1110. This goes to a conjunction node, which gets the same value as or. So that's also going to be the same thing. So yeah, you can see how messy it gets when I try to speed things up a bit. I looked at the time and I'm like, I gotta finish this last one. Okay, let's change this line purple. Now we take its 3 daughters, its 3 babies, and we combine it into its final node. S4. S4. So this takes the conjunction V and it applies it to 2 sentences. It applies it to S3 on the left and it applies it to S1 on the right. And it's an or. So it's true if either one on the left or right is true. So it's true if the left one is true. It's true if and only if U is not an element of the set of X such that X dislikes C prime and V. Or we can just use regular English here, or if U prime is in the set of X such that X is hungry in V. So if it is not the case that U dislikes Carol or U is hungry, that's true if U is not in the set of X such that X dislikes Carol, or U is in the set of X such that X is hungry. If you read the sentence, you can kind of see how the truth conditions come out in the end. That might be intuitive at some point, or it might be intuitive right away. Sorry, that should be a 0. but creating the whole tree is often a little bit of work. So that's the entire tree. It took me about 20 minutes to write in a way that works and make space. Uh, there's a few practice ones on Canvas. Please check the actual page. Alternatively, let me actually show you this before we finish the lecture, because there is 1 minute left and I'm probably going to go a minute over time. And this is the end of this lecture set, but let me show you the page, because some of you might have not seen it yet. There's another way to write this. You don't have to actually write it on the tree itself if you don't want to. So if you don't want to write it on the tree, you can also write it out in list form, which is why we label all of these nodes with numbers. So you can write it out in list form. You can just draw your syntactic tree, and you can just write out like VT1 is appreciates in the set of XY, where X appreciates Y, and just sort of write it out like this. If you prefer doing this, go for it. But at the beginning, sometimes it's nicer to do it on a tree because you can see how everything combines piece by piece. So it's up to you. And then there's some extra practice questions here. So 2 extra trees. It's not that much, but I do have them typed out. And the nice example about these slides is that all of the operators are here. So every single rule you have to use are in these practice questions. All of the rules of F1, negation, conjunction, transitive verbs, intransitive verbs, nouns, sentence truth. So everything you need to practice are in these 2 practice exercises. That's it for today. If you have any questions, you can stick around for a little bit. You can email me, office hours, all that stuff. The questions are exhausting, I know. But yeah, that's all I have for today. Otherwise, I'll see you Friday. And this is the interaction between everything we've done so far in the course in syntax. And yeah, it's scary, but it's also pretty neat.